So just a brief introduction. Dr. Nagesh Kumar completed a Curtis Visiting Professor here in Civil and Construction Engineering at Purdue in May of this year, while he's on sabbatical from the Indian Institute of Science in Bangalore. There he is a professor of civil engineering. He's visiting our College of Ag, now under some funding from the government of India. He is a fellow of all three major Indian science academies. His research spans climate hydrology, water resource systems, remote sensing, deep learning, and evolutionary algorithms. I'm thinking out of that list, at least one of those is probably of interest to you, and maybe more than one. So you see his topic here today, deep learning and geospatial techniques in ag management. Dr. Kumar, thank you very much for being here at Purdue, presenting, and we look forward to what you have to share with us.
Thank you, Professor Dennis, and thank you, Melinda, for arranging all this. I really appreciate all of you coming here in summer. It is supposed to be vacation for you, and still managing your time to come and attend this talk. I really appreciate your time. To be frank, I had a great time for the last one academic year at Purdue. I used to come to this department building very often, even while I was working as Cartesian professor in civil engineering, mainly because my PhD student, Vizzy, she is doing PhD here for 1 year with Bernie and Chris. So she's also working in the CRL for soil erosion and further improving web model that is already available in USDA ARS system. Well, I really take this as a good opportunity for me to briefly mention about the little work that we are doing in this topic. And first of all, before I start talking about it, I must acknowledge my former PhD student, Sudhir Pal. He has done his PhD with me, and what I'm presenting today is based on the work that he has done. And right now he is working as a lead data scientist in a startup company in Bangalore to deal with agricultural management in African nations. So again, before I go into my subject talk, I must sell my institute first. So the institute that I come from, this is called Indian Institute of Science in Bangalore, India. You're most welcome. It's a very lush green campus, small one when compared to Purdue University campus. It's established in 1909 by one famous industrialist as well as a philanthropist, J.N. Tata. You might have heard his name. Tata was a very pioneering industrialist in India, and he conceived this idea of establishing a higher education and research institute in science and engineering. And then the entire land for this institute was given by a princely state, which also had Bangalore city in it. That Mysore royal family, they have donated the land, and government of India afterwards took over and established as Indian Institute of Science. And Tata is so famous in establishing this institute that when you come to Bangalore, if you ask where is Indian Institute of Science, they may not say where it is. But if you say where is Tata Institute, everyone will know where is IISc or Indian Institute of Science. Now it's a premier University of Science and Engineering. It has almost all branches of science and engineering in it, including a medical school that's being established now. It has basically about 6 divisional structure, with each division holding many branches of engineering and science. And because it is Indian Institute of Science, all engineering branches also come under some science division. For example, civil engineering department comes under mechanical sciences division. It has about 42 departments and centers and about 500 faculty members, 5,000 students, but most of them are graduate students, either pursuing masters or PhD. And PhD itself is about 60% of the total students who will be pursuing PhD in IISc. So roughly about one PhD per faculty is the annual productivity in IISc, and about 3,000 publications and things of that kind. But it's also ranked as always as the #1 institute or university in India. And as far as QS ranking is concerned, it is around 220. And in one, I mean, we have to say where we are doing fine, right? So in one QS ranking system called citations per faculty, we stand #1 in QS ranking. Now, let me go into what I want to talk to you today about deep learning applications, deep learning and geospatial techniques applications in the field of agricultural management. Briefly, I will introduce deep learning techniques in case if you're already familiar with it. You can ignore that portion or excuse me if I'm not conveying it as much in detail as you wish to know. Then briefly talk about some of the common deep learning networks that are in vogue. And then I specifically focus on some of the deep learning applications and geospatial techniques in three broad domains with relevant applications in using these data sets. One of them is generating crop maps, specifically soybean crop map, using convolution neural networks and also using multi-temporal Sentinel-1 data sets. I'll tell you why we have to go for that. Then the next one is to talk about multispectral to quasi-hyperspectral data transformation and using convolution neural network regression. But basically, after we generate this hyperspectral data, we try to use them for crop mapping in a very large area of roughly about 7,000 square miles. And the third one is almost like a precision agricultural kind of a thing, where we try to obtain canopy averaged chlorophyll content prediction of pear trees almost for every pear tree or pear orchard using convolutional auto-encoder features of hyperspectral images. I'm planning to take about 30 minutes, and if you think that is too long, you can stop me. Okay, so let me first of all mention about AI that all of you are familiar. I used to joke that since I don't have any intelligence, I use AI to do some work. Artificial intelligence, basically we try to, is a technique which tries to kind of enables machines to mimic the human behavior. And within that, we specifically look for a subset called machine learning. It's a subset of AI techniques which use statistical methods to enable machines to improve with experience or basically evolve as the things happen. And within machine learning, we talk about deep learning. It's a subset of machine learning which make the computation of multi-layer neural networks and try to use that concept to understand any nonlinear process. If the nonlinear process is well defined, it is good. We can try to use some typical analytical methods itself. But if some of the nonlinear processes are not well understood and still we want to model them, then deep learning or these kind of neural network approaches should be able to help us achieve it better. Now, deep learning is basically a computer algorithm that mimics the network of neurons in a brain. It's a subset of machine learning based on artificial neural networks. I briefly talk about that. It's called deep learning because it makes use of deep neural networks. And what is deep neural network? I will briefly mention. And this learning can be supervised, semi-supervised, or unsupervised. And what I'm going to discuss today is basically about supervised learning techniques. Well, if you talk about machine learning in a cartoon like this, we can talk about various machine learning approaches that are in vogue, including some of them for basically classical training. Again, as I mentioned, unsupervised and supervised. We try to use different data compression techniques or image compression techniques like principal component analysis, independent component analysis, etc., or simply the regression analysis. And when we talk about machine learning, we can also talk about reinforcement learning, where we try to use genetic algorithms or some kind of Q-learning, etc., basically evolutionary type of algorithms. Or we can also go for ensemble methods, like basically talking about stacking, bagging, or boosting. Boosting again talks about ADA boost, XG boost, and many other Gaussian boost, etc. Many boosting algorithms are available. They are also pretty good when we talk about ensemble methods for machine learning. But what I would be focusing in today's presentation would be on neural nets and deep learning. And within this, we can talk about convolution neural networks, and again, deep convolution neural networks. We can talk about perceptron, that's a basic neural network concept. Then we can have autoencoders. I'll briefly talk about them. And then we have GAN, are basically generative adversive neural networks. And then we have what we call as recursive neural networks, or RNN. Under that, we talk about LSM, LSTM, etc. Now, I'll start with simple neural network architecture and then talk about various deep learning neural networks frameworks that are available. Now, let us consider this one dot that you are seeing here. That dot, in our human brain terminology, we can try to refer to as a neuron. Okay. And what's happened to the neuron is some external information is coming in, like x1, x2, etc., up to let's say xn, different variables. And that information for each input that is coming in, it is given some weight, multiplied with that, and sum it over, you get the total input that you got. We call it as weighted input of various information. And then that is transformed using a transformation function. That could be any of these functions, sigmoid, ReLU, soft plus, many, cot hyperbolic, and many other transformation functions are there, which will try to transform and give that input at that output. Okay. So that is what's happening in one neuron. If you try to do it, like if you try to put them in this kind of an architecture where we have some neurons here, some neurons here, and some neurons here, and we call them a three-layer network. When the first layer has some information about, let's say, 7 neurons, that means 7 different variables could be the input. And here, if you have about 4 variables as where 4 neurons as the last layer, that could be your output layer, which is trying to give information about 4 different variables. Possibly, input could be rainfall, output could be runoff. As simple as that in hydrology. Okay, and then we have one layer here. This layer is typically referred as hidden layer, and that hidden layer has some number of neurons. So this particular architecture is popularly known as multi-layer neural network architecture, and also known as perceptrons. And when we increase the number of hidden layers, for example, here there's only one hidden layer, here there are 2 layers, and here there are 3 layers. And as you keep on increasing the number of layers between input layer and output layer, what happens is your network architecture will become a lot more complex, but also should be able to handle considerable amount of nonlinear processes, whatever may be the degree of nonlinearity that we may be discussing about. And when we do that, when we try to increase it to such large number of hidden layers, then a shallow neural network becomes a deep neural network. So that's where we try to reuse this technology called DNN, or deep neural network architecture. Now we have many DNNs, or common deep learning networks, that are in vogue in the literature. The first one is basically the deep neural network, as I mentioned to you. And then what happens is, if you try to use on each layer some amount of convolution. Convolution can be in spatial domain, temporal domain, or any other dimension. if you try to do the simple convolution is very simple actually. It's simply a 3 by 3 matrix. You are trying to find the weighted sum of that matrix. As simple as that. If you do that, then what happens is you call them as convolution neural networks. And CNN or convolution neural networks, I'm not referring to the news network channel. Okay, this is convolution neural network. So this type of architecture is extremely useful for image classification or pattern recognition, or even for that matter, voice recognition. Okay, so that's one part of deep learning architecture. Other one is typically called as encoders. These encoders, again, there could be CNN-based encoders, etc., autoencoder-based approaches also. Idea is that we have large amount of data, multidimensional. We try to, first of all, compress them, and then from that, try to extract that information. So that compression is referred to as encoding, and extract the information and then decode it to get the useful information that we require. So encoder-decoder approach is also very popularly known neural network architecture. And the one that I mentioned in the previous slide also is the recurrent neural network. It is specifically useful when we want to talk about time series analysis and forecasting. It could be precipitation forecasting, it could be crop yield forecasting, whatever it is. If you want to talk about time series analysis and forecasting, typical recurrent neural networks will help in achieving that. So in my today's presentation, I shall be talking about convolution neural networks and their derivatives. So that's a brief intro to you about deep learning networks. Now I'll talk about some of the applications or case studies. The first one I want to talk to you about is generating crop maps by applying convolution neural networks on multi-temporal Sentinel-1 data. Let me first of all mention what is Sentinel-1 data. Sentinel-1 tries to give microwave data using synthetic aperture radar. And this data, one major advantage that we have is that it can penetrate through clouds. And during, especially in India, when we talk about rainy season or monsoon season, which is happening right now in India, what happens is that most of the days, there will be cloud cover over entire India. Therefore, optical data will not be of much use to get the information. So we have to go for microwave remote sensing. And this data is available at a very fine spatial resolution as well as temporal resolution. So what I try to do now is that I try to take one study region called Latur district in Maharashtra, India, which is about 700 square miles area. And for that, what we want to do is try to identify what are the different crops that are grown, what is the total area that is grown. And idea is also to come up with that information as early as possible into the crop season, much before we harvest the crop. So that's a study region. And so for supervised classification, what we require is at least for some locations, we should know what is the crop that is already grown there or being grown there. And for that, we refer to in remote sense terminology as a ground truth. And that ground truth came to us from one major project that is taken by Indian Agricultural Research Institute under one major project called Fasal. Fasal itself in Sanskrit or Hindi word means crop yield. So Fasal is an acronym standing for Forecasting Agricultural Output Using Space, Agrometeorology, and Land-Based Observations. And as a part of this project, for entire India, at large number of locations for each crop, we get the location information of what is the crop that is being grown in that location. And that location with the GPS or geocoded data, we refer to them as a particular pixel in an image. So that's one ground truth that we try to use for supervised classification. And as far as satellite data is concerned, Sentinel data is available in a dual pole, that is vertical transmit and horizontal receive. From the satellite, you are sending the signal vertical and receiving it horizontal. That's the way we try to refer to as VH polarization. And VV, vertical transmit and vertical receive polarization. These are the two different polarization data that is available for any given frequency in microwave band. Now that's one data that is used, basically using synthetic aperture data from Sentinel-1B at a spatial resolution of 10 meters. That means every pixel represents 10 meter by 10 meter area, 100 square meters in the ground. And during the crop season, we have about 9 images available for 9 different dates, starting from June 28 up to October 14 before we harvest the crop. So 9 different dates. Idea now is that within a short span of time in the crop season, can we come up with a crop map as reliable as it could be? I mean, if you have all the data that is available, like up to all the 9 dates, then we should be doing very well. But idea is, can we do it, let us say, with 5 images itself or 4 images itself, 4 weeks in advance of the crop harvest? So that's what we try to do experiments here and come up with what's the best way to do it using convolution neural network architecture. There's a big flowchart here. Please don't try to understand everything in it. Treat it as a black box if you don't want to. What we are trying to do here is that we try to provide multi-date dual pole Sentinel-1 data as an input. And the output is for those specific pixels where we know which crop is being already grown. So with that, all the kind of 2D convolution and other things we try to do. And finally, what we are trying to come up with 6 different classes. 5 of them are actually 5 different crops. Okay. And so for the entire district, Latur district, we should be able to come up with a crop map for the entire region. And that, the experiments that we try to do here, I mean, I can give you all the interesting features that if you are interested related to CNN, like kernel size, as I mentioned, 3 by 3, simple 3 by 3 matrix itself will be good enough. Okay. And the activation function, that small f I have shown in the previous slides, is ReLU or rectified linear unit. And kernel regularizer is the L2 and dropout 0.5. And optimizer that we have used is scale gradient descent algorithm. And loss function that we have is categorical cross entropy. And batch size is about 32. These are all some of the parameters that we try to use in that 2D CNN architecture. Now, the experimental setup that we try to do here is that we randomly partition the entire data that is available to us as ground truth into 3 groups, 50% for training, 25% for validation, and 25% for testing. Now, typically, this is what happens in any neural network technology. But the main problem that we faced is with the heterogeneous nature of crop map in that region. 90% of the crop area is by one particular crop, soybean. Like what happens here also. Here mostly we see corn or soybean as the most dominant crops in the region. Okay. So that being the case, what happens is when we try to give the training for the system, for one class, we have large amount of ground truth. For other classes, we have small amount of ground truth. That will create some problem in training the deep learning neural networks. So to balance the difference in number of samples for different classes, we use what we call as class weight approach, which is available in sklearn package in Python. So we try to use that to overcome the difficulty. Now, the kind of experiment that we did is that we try to use VH polarization data or VV polarization data, or both of them using their ratios. And more importantly, please look at this portion. Can we come up by using only 7 dates, that is 3 weeks before harvest, what is the amount of accuracy that we are achieving, versus only few 6 dates, that is 5 weeks before harvest, and 7 weeks before harvest, what is the kind of accuracy that we are achieving? So that is what we try to assess using various experimental techniques that we try to use by using this CNN architecture. Now, I'll not trouble you in going through all the details, but at the summary, I can say that even when we are talking about 7 weeks before harvest, we could come up with a reliable crop map like this. I'll show you that in a minute. But before that, this is just for the sake of people like working in remote sensing. If you try to use VH-VV data, okay, and the ratio during different crop phenological stages, as shown in the dates here, how the VH-VV will vary for different crops. Cotton fallow is no crop, or basically no crop does not mean that it is fallow. In my terminology here, it could be urban area also. Anything that is non-crop area, I left it in one group. Okay, so if we try to use this data set and come up with a classified map, this map is showing, as you can see, it's predominantly green, and that green is soybean crop. Okay, and then we have other crops. I gave the Indian names there, tur, dal, etc. But actually, its actual name tur is PGNP, and jowar is one Indian name. The crop name here is sorghum, and so on. Okay, so these are the different crops, and also we have, for some region in the tray portion, mixed crop. That means soybean and PGNP are grown together in a few locations. So those are also identified. The accuracy that we can achieve with the 2D CNN, both with VH and VV polarization data, is very good and quite stable. And that's where we try to find out and say that, synthetic aperture radar that is available, cloud free, that's the most important thing for us, because during this entire period that I mentioned to you, we will pray to God that at least we'll have one cloud free image, which is very difficult to get. Whereas with microwave, we don't have to worry about it. We get a good number of microwave data. So, we always used to say when we started working on microwave remote sensing, maybe I'm a very old guy. I started working it sometime in 1990. That time we used to think that, we require 5 sensors that we have to classify an image optical data. And to classify a microwave, we also require our 6th sense. And if we don't, then try to use convolution neural networks. So that's what we try to do here and come up with image classification. But now what I'm trying to do is I try to use these deep learning applications for hyperspectral image processing. And I know that many of you may be familiar with it, but just for the heck of it, I'll take one slide to explain what I mean by hyperspectral versus multispectral. Please look at this cartoon here. What we are trying to see here is about 500 to 2500 nanometer wavelength region in electromagnetic radiation spectrum. That's basically optical data and both visible and infrared data. Okay. Now in the data, if you try to look at Landsat ETM, Landsat Enhanced Thematic Mapper, which has been one of the most popular satellite data that has been used extensively, it has about 7 spectral bands shown in yellow colors here. Okay. When compared to that, if we try to have hyperspectral images for the same wavelength region on x-axis, okay, we will have about 200 to 300 spectral bands, or in some cases, especially if we try to use NASA's aerial remote sensing for hyperspectral, that we can talk about 400 spectral bands. The major advantage is we get a very detailed spectral information of any particular feature that we are interested in. In our case, mainly the crop type, crop stage, and crop condition. They could be monitored better with a hyperspectral remote sensing when compared to multispectral remote sensing. So that's the concept that we try to use. Of course, we are talking about a huge amount of data. Even for one small region, one image or one band, if you try to call about, then you have 400 layers or 400 images. So we are talking about petabytes, if not zettabytes of data that we have to handle as far as hyperspectral data is concerned. So There are two experiments that I try to demonstrate and try to show you as case studies as part of this work here. Okay. The one that I want to talk to you is when we started moving from multispectral to hyperspectral data. One of the first satellites that was launched as far as satellite remote sensing using hyperspectral sensing system is Hyperion, launched by NASA. It's no longer functional now, but that data was one game changer at the time. So we try to look at Hyperion data, and we also looked at Landsat ETM data, which is available at a very good spatial resolution and also available at a very good temporal resolution, whereas Hyperion data is not. It is available only at a few locations at a given time. So our idea is that if you have a Hyperion data for one location or for one region, can we try to, for the same reason, if you also have Landsat data, then train that data set and from Landsat data, synthetically create hyperspectral data and validate it for that region. If it is doing well, use that developed neural network architecture to do it for many other regions where we don't have hyperspectral data, but synthetically generate. That's what we call as quasi-hyperspectral data. Okay. So that's what we try to do using convolution neural network regression in this approach. The idea is that use that small portion for which we have the hyperspectral data as well as Landsat ETM data and train the system and use that system for the entire region of your interest. And the interest that I'm talking about is roughly about 7,000 square miles. So there are some architectures that are already available in Python to deal with this, developed like FITA, that is pseudo hyperspectral image transformation algorithm. And then we try to use stepwise linear regression. We also try to use support vector regression and our main baby here, convolution neural network regression. So and try to compare them and try to see how that quasi-hyperspectral data is performing with some statistical metrics. And once we are done with it, when we can generate for a large region, we try to use it for crop classification or get the crop information for that region. So we try to use our information here is Landsat ETM data, 6 bands, 7th band is thermal, we did not use it. And then Hyperion data, which is about 170 spectral bands. So we have about 50% was used for training and 50% was used for testing. And because it is image and large number of pixels, training data is very large. Okay. And we try to use existing approaches and our convolution neural network regression, develop the model, test it and validate it. And then for the regions where we don't have hyperspectral data, provide Landsat ETM data and get the quasi-hyperspectral data, use the data for crop classification and see how well we are doing. So there are two things that we are trying to do here. One, first of all, what kind of convolution network architecture is good. Second, and once we generate the data, how well it is doing as far as crop classification is concerned. Okay. So this is a typical CNNR or convolution neural network regression approach. So as you can make out, we are trying to provide 6 bands Landsat ETM data as input, and we are trying to generate 170 bands Hyperion data as output. Okay, these are the different CNNR architectures that we have tried. We call them as model 1, model 2, etc. up to model 6. And we try to compare them with existing approaches also and try to say, I'll come back to that in a minute. Yeah, and try to say which one is doing better. This table summarizes, we have to sell our approach. So we try to say that CNNR model 2 is doing good in terms of its performance in overall accuracy, kappa statistic, and also other parameters. Now, before I go into it, let me just briefly mention what we are trying to do here. What you are seeing is a Hyperion image here, okay? And this image is a 170 spectral bands, but I used 3 of them to prepare what we call a standard false color composite, okay? And in the standard false color composite, whatever you see in red color is healthy vegetation. Okay? And for that, this is Landsat ETM data covering this region. Okay? And this is one of our very popular website where we try to provide a lot of information. This is called Berambadi watershed. You don't have to pronounce it, but if you can type it, you'll get a lot of information about it. It is one of our critical zone observatories where we try to monitor agriculture, soil moisture, and many other parameters extensively with a lot of information. And we have very good collaboration from US, France, UK, and many other places. All of them come to IISc not to visit IISc, but to visit this website, to visit this particular field site. So for this, we have a lot of ground truth data, and we try to use that and train the network. See, I told you this is one particular state called Karnataka, which is roughly about 7,000 square miles. Okay, and only for this small portion, we have Hyperion image. And we also have Landsat image. So we train our CNNR using this portion and try to generate the Hyperion data for this entire region. And what are the green dots that you are seeing here are the places where we have ground truth of different crops that are grown in those locations. That is what we try to use afterwards to generate the quasi-Hyperion data. Okay, so if you see Landsat ETM spectral reflectance curve for various crops, okay, they look like this. But what is very interesting is if you try to see the same spectral reflectance curve for the same pixels using Hyperion data, you can get this much detailed information. Small variations in every wavelength is available here. That's a major advantage to talk about crop information. So the idea is to generate or try to utilize this information and then generate the hyperspectral images, quasi-hyperspectral images. And we try to use that to compress classify the entire area. And we found that we could get a very good accuracy when compared to simply using Landsat data. Using Landsat data only generate quasi-Hyperion data. And from that, you try to classify the images, we get excellent accuracy. That's what we found it to be. Now, the last topic that I want to talk to you is about these pears that you might be having it in your breakfast or in your snack. Idea is here to get the canopy averaged chlorophyll content for every orchard at a very high accuracy. I'm talking about precision agriculture here. So I'm trying to get information at about 5 centimeter accuracy. For every 5 centimeter by 5 centimeter pixel, I wish to get the information about chlorophyll content. Chlorophyll content is a very good information, which is actually kind of an representation of crop condition and also the amount of fruits that particular plant is likely to bear or yield. Okay, so that's a concept that we try to use here. And again, the concept that I talked about auto encoders. So convolution auto encoder approach was used here to do the work. Now, there is a lot of ground truth that is used here. It is not mine, it is available. Any of us can use it. And let me briefly mention about what is that we are trying to use here. Okay, so here, this is actually a site in Belgium. Okay, and this is a small location where a lot of pear orchards are there, and they are being monitored using drones. Okay, and you can see in a Google Earth map, each orchard can be seen very clearly. There are rows here, rows of orchards. Okay, and idea is that we try to get this information using a drone. Actually, it's a very good drone. I mean, from American company only, Hedball, micro hyperspec. It has a spectral range of 400 to 1000 nanometers, and it has about 326 spectral bands, and the spatial resolution is 5 centimeters. Okay, that means maybe almost for every leaf we can get the information. And then we try to do this. I mean, this is a drone, so we can decide whenever we want to fly it, we can fly it. Okay, so we try to get it in multiple dates like this, starting from different growth stages of that pear orchard, fruit fall after flowering, second fruit fall, fruit growth, and ripening, various crop phenological stages, we try to get this information. And there are about 33 experimental trees for which we try to get the information. Now, where is the ground truth? Ground truth in terms of canopy averaged chlorophyll content. For that, we try to extract some leaves from the tree, collect them, put them in ice chest, bring them to the lab, and do the chemical analysis. Acetone was used as a solvent to bring chlorophyll into solution. And on that solution, if we try to get using a spectrophotometer, if we try to use specifically two wavelengths like 662 and 645 nanometers, we should be able to get very good information about chlorophyll content. So that's the chlorophyll content that we try to use as a ground truth for a few pixels or for a few orchards where we have collected the leaf samples. I repeat, I'm using we, but I haven't done it. Okay, it's all available in this particular website related to this particular experimental set. Okay, so we try to use the data, and we try to use this hyperspectral images. All the 350 are there. Some of them are noisy bands, they are removed. So 264 spectral bands were used. And those bands are used in again in 2D convolution architecture to come up with the canopy averaged chlorophyll content for every pixel after the training is complete. So just to give you an idea, just to summarize the results that came out, this is a basic experiment that we did it for about 10 random trials. We have used various approaches to approaches in deep learning neural network approaches to come up with the best way to get the canopy averaged chlorophyll content estimation. And once that is done, then these are some reference trees or reference orchards for which we have all the data available in terms of ground truth. And using that, we try to get the information in detail. But then we try to get the information for all these orchards. And that we try to do by calling it as predicted canopy averaged chlorophyll content. Idea is that for every plant, when we obtain this information, if we have also obtained the yield, that is number of fruits that are coming from the particular tree or particular orchard, then we can as well relate the CACC with the yield and then talk about yield prediction itself in advance during flowering stage or much before, talk about what is the yield that we are likely to get. Not only that, it's not only about yield, but if we are estimating that some of the orchards are in trouble or one particular plant, a tree is in trouble in terms of its yield, then we can try to see what can be done. What is the corrective mechanism? Is it pest infected, or is it not having the water that is required? And things of that kind can be monitored. So we can try to talk about monitoring and managing at a plant level for each of these pear trees. That's the final outcome of this study. So that's what we did it for different months in the pear growth season and came up with this kind of CACC data in advance and to tell what's likely to happen in terms of crop condition and crop yield. Well, that's what I wanted to talk to you. Deep learning, as I mentioned, has a tremendous potential to improve our understanding and modeling of highly nonlinear processes. Deep learning can play a vital role in knowledge extraction by huge data mining of geospatial data, which is essential for sustainable agricultural management. My last slide is to sell myself. In case if you are interested, this book is just out of shelf. Last month it was published. It's called, we try to make it as generic as possible. We said artificial intelligence and machine learning techniques in engineering and management. Although I'm a civil engineer, I try to say that I try to briefly talk about each of the other domains, including management, and come up. In case if you know AI and ML, it's not for you. This is basically kind of a textbook with classroom examples for each of the techniques that we try to mention and how we can try to learn and adopt. And my last chapter is very interesting because I have to mention about my last chapter where I worked for more than 1 year. Is just collection of literature in various domains of engineering and management, what is happening, state of the art, and where we stand in terms of using those techniques to solve some of the serious problems, mainly because of nonlinearity or lack of understanding of nonlinearity that may be there in the system. So with that, I stop here and thank you very much and really appreciate your patience in listening to it.